Hi there, welcome to the last part of this series of videos. So we're going to go through the questions on amino acid chromatography. So it's question 38, valine, citrulline and hydroxyproline and glutamic acid are amino acids that are normally found in considerable amounts in urine. Following certain diets can result in a change in the amino acids present in the urine of some people. Plan a method to compare the amino acids present in the urine of a person who's been following one of these diets and a person who has not. Okay, so first of all, comparing amino acids, think about the experiment you've done. You're going to need to use a chromatography experiment. So the first thing was to identify that you'd use chromatography. It's obvious because you've got the title just here, but if you just come across the question without the heading, first step is to identify that you would use chromatography. Remember that you can use diagrams, you can draw little pictures if you want to. So I'm going to draw a little picture here of what it's going to look like as well. So if we draw a pencil line along the bottom here, and we're going to put little samples of our different various amino acids along the bottom. So if you manage to separate out your amino acids, you could put one on each dot. If you haven't separated out the amino acids, you could just put the urine of each person on each dot. Okay, then you're going to stand that in a solvent. So let's put it into a beaker. Okay, and we've got the solvent at the bottom of the beaker. The solvent must be lower than our pencil line. So here's our solvent here, and our solvent will soak up the paper up here. We stop it before the solvent gets to the top and we draw a line. That's our solvent front. And we're going to end up with the dots that show how far it's moved up the paper. Okay. So first of all, you're going to put first of all, actually, step number one, you're going to draw the origin line and pencil. Step two, you're going to put the samples, it doesn't say they've been separated out, so put the samples of number two, put the samples of urine on the origin line. Number three, you're going to stand it in a solvent. And then what will happen is that you will separate the amino acids. So probably what will happen is if this is person number one, then they might contain a few different amino acids, which might separate into blobs like that. This might be person number two, and it might separate into blobs. Maybe one in line with that one in line with that one, and the third one might go further. Okay, so it's going to separate out into different spots. Remember, let's separate the amino acids by running the chromatography. Remember that anyone that moves further is because it's more soluble, so they move further if more soluble in the solvent. Okay, and then number five, because you have used amino acids you can't see, it's not like using pen ink, so you need to spray them with ninhydrin to make the spots visible. And then you compare the pattern. So in this one, for example, you can see that they've got two amino acids that are the same. That one's the same, that one's the same. These have moved different distances. They've obviously got different solubilities. They're obviously different ones just there. One more thing that we could say, just to add detail to what you know about amino acid chromatography, is that when you use the solvent, when you're using amino acids, the solvent you use can be aqueous or it can be hydrophilic. Right. And that's that one. So it's just knowing your method really for amino acid chromatography. Number 39, a student investigates the solutions XYZ using paper chromatography. The results are shown below. Which of the following options A to D is the RF value of Z? So you need to know how to calculate RF values. So in order to calculate RF values, you do the distance that's moved by the dot, which is the solute, divided by the distance that's moved by the solvent. Okay, so we were looking specifically at Z for this question. It asked you about Z. So you need to measure with a ruler how far did the solvent move, and that's your number for the bottom here. And you need to measure how far was it that the solute moved, and that's your number for here. So if I call that number A and that distance B, you're going to do A divided by B. Okay, and you need to actually measure those with a ruler on your exam paper and work out one of those numbers, A divided by B, and see what you get. And your answer should roughly match one of these, and the one that it should match is A 0.63. Okay, so you just make sure you do your measurements, one divided by the other. It's the smaller number divided by the bigger number every time. And you should always get a number that's near one of the ones in the options. Number 40, on figure 1.1, draw a circle around the R group. So we don't know the R group of leucine, okay, but we know that an amino acid has a central carbon. We know that it has an amino group on one side. We know that it has a carboxylic acid group on one side. We know it has an H, usually above, but they've actually drawn it below. It doesn't matter. Where's the bit that we don't know? That must be the R group. So all of this is also attached where we would normally have just written R. So that must be your R group just there. So your answer is the green circle. Students use thin layer chromatography to separate leucine from other amino acids, and the chromatogram they produced is shown in figure 1.2. So this one is just drawn the other way around, okay? They've just turned the paper the other way around. So if you wanted to turn your paper sideways so that it was in a beaker like this, the solvent would have been filled up to here, and the solvent will have soaked this way up the paper. They've just turned it on its side, okay? If you were then doing your measurements ready for your RF value, you'd have measured origin to solvent front, which is that one there. Okay, and then up to the solute for whichever one you're interested in. So this question asked you, what can you conclude about the chemical properties of leucine and amino acid X? So leucine and amino acid X are here and here. So one of them's moved from the origin up to there, and the other one's moved from the origin up to there. We should really measure to the middle of the spot. And they've moved roughly the same amount, so they must be more or less the same solubility. You could have said leucine solubility is slightly more, but you can't say it's more. It's not massively more. It's not really significant. Okay, so ideally they have very similar solubility. You could say same solubility, or you could say leucine's was slightly higher. Amino acid Z was in the mixture analysed by the students. It's not shown on the chromatogram in figure 1.2. Amino acid Z has an RF value of 0.2 lower than amino acid Y. So first of all, you're going to need to work out what is the RF value of Y. Okay, then it says that the RF value of Z, the RF value of Z is whatever it was for Y minus 0.20. It said it was 0.2 less. Okay, and then you needed to place a dot on the chromatogram to show the distance moved. So step one, what's the RF of Y? So how far did the solute move divided by how far the solvent moved? So you needed to measure this question. Let's do another colour. First of all, on your paper, please make sure you've measured the distance from the origin to the middle of that dot and the distance from the origin up to the solvent front there. And you should have a number for that and a number for that. And we're going to do A divided by B. Okay, I can't measure it on my screen, but make sure you do that on your paper. So the first part here, RF of y, you're going to do value A divided by value B, the distance moved by the solute divided by the distance moved by the solvent. And whatever numbers you get for that, you should end up with an RF value of approximately 0.5. Okay, make sure you actually work that out yourself to check you can get that. So then it told us that the RF value of Z was whatever it was for Y minus 0.20. So 0.5 minus 0.20, and you should get 0.3. So the RF of Z is 0.3. Now it asks us to place a dot. So what we want to find is we need to know what distance did it move from the origin. So if the RF is the distance moved by the solute divided by the distance moved by the solvent, what we want to find is how far did the solute move. So we need to rearrange our equation to find that. So solute equals RF divided by the distance moved by the solvent. So then we know that the distance moved, should put distance on each of these really, the distance moved by the solute equals, we're trying to find it out for Z. So the distance moved by solute dead is Z is RF, which we just found out to be 0.3, divided by the distance moved by your solvent. So you're going to have to go back to your picture and measure, well, you've already measured it really, but how far did the solvent move? That was your value B, wasn't it? The solvent moved from the origin up to the solvent front there. Okay, so divided by whatever you had for B, which should have been approximately, let's have a look. Oh, I've just realised I've rearranged this wrong. I beg your pardon. So that should have been times the solvent. Sorry, I can't rearrange equations. Silly me. So it'd be 0.3 times the distance moved by the solvent, and the solvent you should have measured was about 5 centimeters or 50 millimeters. So we're going to times it by 5, and that should equal 1.5. And then the last step you should have done, so let's just put these in order. Make sure the examiner knows the order your workings go in. Separate them off if they're merging into each other like mine. So the answer 1.5, you then had to plot it on. So you just measured 1.5 from there, and you should have drawn your X there and labelled it Z. So there was a lot to that one. It was tricky, long one. And that's the end of the question paper. Well done, well done.